All right, today we're going to be in the linear regression packet, and we are going to be on page 5 and 6 talking about correlation. So a measure of how well a regression fits a set of data is called correlation. The correlation coefficient is a value between -1 and 1, which indicates how close the data is to the graph of regression equation. The closer the correlation coefficient is to 1 or -1, the stronger the relationship is between the two variables. The variable r is used to represent the correlation coefficient. So if you have a positive correlation, okay, a correlation like this, and it's really strong, that correlation coefficient is going to be closer to 1. All right, if it has a negative correlation coefficient, okay, and it's really strong, that's going to be closer to -1. And then no correlation at all is going to be close to 0. All right, so that's pretty much what all of that means. So number 1, we're going to determine whether the points in the scattered plot have a positive correlation, a negative correlation, or no correlation. 4 possible R values are given, and we want to circle the R value that we think is most appropriate. All right, so looking at A. All right, so the dots are going downward. Okay, so that shows us that this is a negative correlation. So now we have to determine a R value. So since it's negative, it has a negative correlation, I can automatically mark out the first 2 choices because they're positive and we need something negative. All right, next, we can notice that our dots have a pretty strong relationship because they're kind of all going down and it kind of looks like a line even though it's not because it's made of dots. So that shows me that that is a strong correlation. So I'm going to go with the decimal that is closer to a -1, which would be -0.9. All right, B, these dots are all going up. So they're all going in a positive direction. So that means that this has a positive correlation. So to pick my correlation coefficient, I can cancel out the negative ones. And then there is a relationship between the dots because they are all going up. And it kind of looks like a line when you look at it, even though it's made of dots. So that's a strong correlation. So I'm going to pick the decimal that's closer to a +1. All right, and then C, there's no correlation here between the data points. Okay, they're kind of all over the place, so there's no correlation. And I want to pick the correlation coefficient that's closest to 0, which is going to be 0.01. All right, now we're going to go to Desmos and we are going to make a table and we are going to put these values in, and I'm going to show you how to find the correlation coefficient from there. So we're going to go to Desmos. Now that we're in Desmos, I'm going to add a table and I'm going to put those dots in, or those points in. So 23, 23, 1, 2, and 3, 4. All right, so if I zoom out, there's my data points. Now to find the correlation coefficient, we're going to use what we did yesterday, or in the previous video. So I'm going to do the same formula, y1, squiggly line, m, x1 plus b. All right, and this gives us our R value. Okay, we're not worried about R squared. That's something different. Today we're just worried about the R. And our R is 1. And 1 and -1 are the strongest relationships that you can have. So I would say that this data table has a really strong correlation because our correlation coefficient is 1. So going back, we're going to interpret the correlation coefficient. So we're going to say R equals 1. And that's very positive and strong linear correlation. All right, so now we're going to look at an example. So a group of friends completed a survey about their monthly income and how much they pay for rent each month. The table shows the results below. So in our X column, this is their net income, so how much money they're bringing in. And then this is what they're spending on rent. That would be our Y value. So number 1 asks for our independent and dependent. So independent is our X-axis, so that is their net income. And then our dependent is our Y, which is going to be the rent. All right, so if we flip over to page 6, it wants us to sketch and label the scattered plot of data after graphing it in Desmos. Okay, so first I'm going to graph it on my paper before I go over to Desmos. So our first point is 1,400 and 450. So here's 1,400, here's 450, so those meet right there. Okay, next is 1,550 and 505. So that's going to be right here, and then 505. All right, 2,545. 2,600 and 715. $3,930. And 3,400 and 1,000. All right, so now that it's graphed there, I'm going to go over to Desmos and type this table in. So I'm going to add a table. So 1,400, 450, 1,550, 505. 2,545, 2,600, 715, 3,000, 930, 3,400, and 1,000. All right, so that is our graph. Now we need to find the linear or the line of best fit equation and the correlation coefficient. So I'm going to type my formula in. So then I have my correlation coefficient, my M, and my B. And so now I'm going to write that on my paper. All right, so we skipped 3, but on 4, okay, I wrote my linear regression equation, and I wrote my correlation coefficient. So number 3 says, do you think a linear regression equation would be best for this situation? And we're going to say yes, because the graph appears to be linear, because all of our dots are going up. It looks kind of like a line. All right, so the correlation coefficient R indicates the type, positive or negative, and strength of the relationship that may exist in a given set of data points. The correlation or the coefficient of determination, R squared, okay, that's supposed to be an R squared, measures how well the graph of regression fits the data. It represents a percentage of variation of the observed values of data points from their predicted values. All right, so another example. The amount of antibiotic that remains in your body over a period of time varies from one drug to the next. The table given shows the amount of antibiotic X that remains in your body over a period of 2 days. Determine and interpret the linear regression equation fit of this data set. All right, so before we do that, I'm going to graph it down here at the bottom. So 0, 60, 6, 36, 12, 22, 18, 13, 24, 7.8, 30, 4.7, 36, 2.8, 42, 1.7, 48 is 1. All right, just by looking at this, we can see that this data has a curve to it when we graph it. So it's not necessarily a linear regression line is not going to be the best fit for this data because it's not being represented by, or the data is not in a linear representation. Okay, it's more curved. But we're going to go through with it so that we can show, okay, using like the actual numbers, we can show that a line of best fit is not going to be best for this data. So we're going to plug this table into Desmos. So we have 0, 60, 6, 36, 12, 22, 18, 13, 24, 7.8, 30, 4.7, 36, 2.8, 42, 1.7, 48, 1. All right, so that's what our graph looks like, which looks really similar to what we just graphed on our paper. Now I'm going to put the formula in. And as you can see, that line doesn't really hit a lot of those points, and it's not super close to a lot of those points because the data points come out in a curve. All right, so now we're going to take that information and put it on our paper. So our line of best fit equation is negative 1.07x plus 42.26 . All right, compute and interpret the correlation coefficient. So that's our correlation coefficient, negative 0.8832, and that's negative correlation. And to interpret it, okay, we can say that linear would not be the best fit. Because the graph looks like an exponential function. Okay, you may remember that from last year in your Algebra 2 class. Y'all talked about the function families, and exponential was one of those families you talked about. So that completes the notes for correlation coefficients.